So as we have already discussed, that a routing table can be either static or dynamic. Fine. So in last class, we have seen that the static table is one with manual entries and dynamic table is updated periodically. Fine. So whenever there is a change somewhere in the internet, so there we need to change the table entries, and both static as well as dynamic entries we can go for. However, there are certain issues that we will discuss today, because we are going to discuss a very important topic of this unit called unicasting routing protocols. So this unicast routing protocols can be divided into intradomain routing and interdomain routing. And we are going to discuss all these things and some of the popular protocols in this unicast category. Fine. So you see, today an internet needs dynamic routing tables. Fine. So the tables need to be updated as soon as there is a change in the internet. Now you understand. Now tell me one thing, when I am saying internet, is it small I internet or capital I internet? I'll see, you can write. Is it small I internet or capital I internet? What I said was that in current situation, the internet needs dynamic routing tables. Fine, because this needs to be updated. Very good, very good. So it is small I internet. Fine, because we are talking about internetworking. There are a lot of networks, and they are connected with each other. Fine. So capital I internet is considered to be one of the example of the internet what we are talking about, that is small I internet. Okay. So the same thing is there. So as I told you that in current scenario, internet needs dynamic routing because the real-time scenario cannot adjust with the static routing tables. So, but the problem is that these routing, even though it is dynamic in nature, they need to be updated when a router is down, or they need to be updated when a better route has been found. So all these things are in real time. So that's why I'm saying that the dynamic routing table needs to be done. Now, what is the application? So let us see that if there is a router in Jaipur, fine, and there is a router in Delhi. So the router in Jaipur, whenever it tries to communicate further, it has to go via the router that is situated in Delhi. Why the router in Jaipur needs to have dynamic routing schemes in it? Because maybe possible at certain point of time, the router that is situated in Delhi goes down. Okay, so it goes down. In that case, it becomes very difficult for so what will happen basically, that the router in Jaipur will unnecessarily try again and again to send the data or packets. Fine, and that is not required. Fine. So as is given over here, a routing protocol can be defined as a combination of rules and procedures that lets the routers in the internet. Please have this in mind that I am talking about small I internet, and we are very much clear about the difference between small I and capital I internet. So a routing protocol, it is a combination of rules and procedures that lets routers in the internet inform each other of changes. So definitely there will be an initialization, there will be an updating mechanism, there will be definitely a sharing mechanism. So how the updation, sharing and deletion of the entries are done dynamically, that we will see in today's lecture. So most important part before going towards understanding the different categories of routing protocols, what we are going to discuss over here is unicast routing. Okay, so in case of unicast routing, very important to understand the concept of optimization. See, a router receives a packet from a network, fine, and passes it to another network. Okay, so a router is usually attached to several networks, we can see. So the questions that arise are, first, So when the router receives the packets, to which network should it pass the packets? Because I already told you that the router is connected to different networks. Second question is, which of the available pathways is the optimum one? Fine. And third, very important, how can you define the term optimum? So optimization could be in terms of, like in previous lecture, I was telling you that when we discuss about routing, a lot of other terminologies come, like how you decide on which route you have to send a particular packet. So that route discovery and route decision making will be done on the basis of optimality principle. And that optimum definition will be in terms of either link quality characteristics, either cost of transmission, or some other parameters. We will discuss those parameters as we go further in understanding the different routing protocols. But first, we should understand the current scenario. Okay, so I already told you that routing protocol in current scenario, when we say the internet, so internet is very huge. Okay, the network in current scenario, then in a particular network, if we see the network of our college itself, LNMIIT, there are only how many, at minimum 1,000 number of people are there. Okay, so even that small network is very huge in nature. So you can understand, if we talk about different networks that are deployed and operating throughout the world. So when we say that the internet is huge, in that case, one routing protocol, if you want to use it, becomes very difficult, because there are different areas. Those areas are of different characteristics. Some may be denser in nature, some may be sparse in nature. Okay, and maybe possible that some of the areas need extra special care because of the reason that they may be remote. There may be some remote location. Some regions need that special care to be done very minimally, because the users or the hosts or routers, they are very intelligent as compared to, so as compared to the routers or hosts which are located at some other places. Okay, so these are the different scenarios. So before discussing about unicast routing protocols in detail, we have to first understand the concept of autonomous system. So what we do is we divide this big internet into small autonomous systems. What are those autonomous systems? So those autonomous systems are a group of networks and routers under the authority of a single administration. What does it mean? That we have different autonomous systems, we'll see, and in those autonomous systems there are different networks, different routers, different hosts, and they will be taken care by a single administrator. What does it mean? That one administrator is always assigned to an autonomous system, and whenever you want to communicate between two autonomous systems, that communication will be done via that administrator only. So in this sense, what is happening, that let us suppose one autonomous system is India and one autonomous system is USA or some other country. In that case, the president of that particular country we can assign to be the administrator. Okay, so similar case, we are creating different autonomous systems. Now, two important topics are there, or terms are there: intradomain routing and interdomain routing. So it is similar to intranet and internet. So when I say intradomain routing means, so the routing is taking place inside an autonomous system. Okay, and interdomain means when the routing is taking place between two or more autonomous systems. Okay, it is very simple. There is no scientific mechanisms behind these two terms. So just let you understand. But it is very important, because further the intradomain and interdomain routing there are different protocols associated. Now I must tell you that these protocols are not limited. There are other protocols also in intradomain and interdomain, but these three are very popular protocols and they are widely used. So that's why I'm going to discuss we are going to discuss these three protocols. So one is distance vector and link state, which comes under intradomain routing, and path vector that comes under interdomain routing. Fine. Now there are three different topics: RIP, OSPF, and BGP written over here to let you understand very simply that RIP can be understood as the implementation of distance vector. So distance vector, link state, and path vector, these are the routing protocols as guidelines, and other routing protocols further are developed. So like RIP is an implementation of the guidelines of distance vector, OSPF is the implementation of the guidelines of link state routing, and BGP is the implementation of path vector routing. Okay, and this BGP is very important. We will see in coming slides that this BGP is basically doing the interdomain routing. Fine. So let us start with our first routing protocol, that is called the DVR. In short, that is the distance vector. So in distance vector, to let you understand, the least cost route between any two nodes is the route with minimum distance. Okay, that is the method that is utilized. What does it mean? That a node can communicate to another node based on the least cost route. How can you decide this least cost? Based on the minimum distance between those two routers. Okay, so as the name suggests also, that each node maintains a vector. Herein we are defining this vector as a table of minimum distances to every other node. So how you can understand distance vector routing, I can give you an example. So we can think of nodes as the cities. This is one of the figures you can see over here. So you can understand or you can think of these A, B, C, D, E nodes as the cities. They are situated in an area, and these lines can be understood as the roads connecting them. Okay, so the table that you are drawing over here, this table can be used by a tourist or some other people who wants to roam among these cities. Fine. So in that case, I can use, or that tourist can use, this particular table and understand that for going from A to a particular node C, how much cost is involved, or metric, or what is the distance, okay, in this distance vector routing. Fine. So it has different states. Now this, what you see over here, this figure shows the final routing tables of each and every node. Now whenever we discuss the routing algorithms, we assume that all the nodes are routers, okay, because the routing will be done by routers only. So A, B, C, D, and E, these 5 nodes are routers, and each and every table which are given over here are finally made tables which can be referenced. But now to understand distance vector, we should understand how these tables are made. So first step is the initialization step. Okay, so herein we are going to discuss how the routing tables are created. So in this particular figure, as I told you, this is a very stable kind of figure. Okay, every node knows how to roam around and reach each and every node, and what is the cost involved. Definitely the cost here is in terms of distance. However, this is not the case. So in beginning, each node can only know the distance between itself and its immediate neighbors. So A can only know the distance from immediate neighbors like B, C, and D. A cannot have the knowledge of E. Fine. So initially, A makes its table based on this parameter. So what is that? What is that? First, from A, for A's table, the first column says the destination 2. So from A, if A wants to go to A, definitely the distance is 0. So that is the cost. Next hop, because it is an immediate neighbor or the node itself, there is no next hop. So if B wants, from A you want to go to B, the distance is 5. C, it is 2. D, it is 3. And E, it is infinity. Now you must understand that whenever I say infinity, it is the distance for any entry that is not a neighbor of a particular node. Since E is not a node of A, I will assign it as infinity initially when I am creating a routing table. Fine. Infinity suggests that this node E is not reachable directly from A. We have to, A has to send certain packets to E using that some other intermediate node. Okay, so that we will see in coming slides, that how that information comes to A key, what is the distance of E from A. Okay. Second is the sharing. Okay. So the whole idea when I talk about sharing, so first initially each and every node knows the distance from immediate neighbors. You can see each and every node knows the distance from immediate neighbors. Okay, you see, because of I have taken the screenshot, this is empty. It is not a very big deal. Like these routing tables are created, you can understand and you can create this C's routing table. So second point comes is sharing. Once initial table is known, so the whole idea of DVR is the sharing of information between neighbors. So for instance, if you observe in this figure, node A does not know even about E. Okay. However, node C knows about the existence of E. If A doesn't know anything about E, even this is just for the sake of you understanding how it is done. I have entered E. E should not be even entered in this routing table. Fine. So A doesn't know the existence of E. However, C knows, B knows. Now we have to ensure that from by going from A to E, A takes the shortest path. Okay. So that we have to discuss while doing this sharing operation. Okay. So what happens basically that each and node shares its routing table with its immediate neighbors periodically, and when there is a change in the network. So what is the problem involved? So how much of the table must be shared with each other? Okay, so if one observes carefully, a node is not aware of neighbors table. The best solution for each node is to send its entire table to the neighbor and let neighbor decide which column to use and which to discard. However, you see the third column over here is not useful for the neighbor. Why? Because when neighbor receives this particular table, the column needs to be replaced with the sender's name. So if B receives some information from A, so this particular column is the via information. So A wants to go to E, here C will come. Okay, so likewise we are doing the sharing operation. So what is the solution? And instead of sending the whole table, why not to send only 2 columns which are necessary? Because of obvious fact that we have discussed in previous lectures also, traffic is already there. Why you are increasing the amount of the size of the message you are sending? Fine. So just send 2 columns which are very important. The first column 2 and the second column, that is cost. Fine. So what are the few so sharing, basically what we are doing by sharing, we are sharing the first 2 columns over here. So there are certain points that we need to emphasize. So as we know from mathematics, point number 1 is that as we know from mathematics that when we add number to infinity, the answer is infinity itself. Second point specifies that whenever the modified table we have, it shows how to reach A from A via C. Okay, if A needs to reach itself via C, it needs to go to C and come back, and that is not required. Okay, so we will see these points in the third important step, that is called updating. So what happens in updating? Basically, whenever a node receives a 2-column table from a neighbor, it needs to update its routing table. So what are the steps involved? First, the receiving nodes needs to add the cost between itself and the sending node. Okay, then the receiving node needs to add the name of the sending node to each row as the third column. Then third, the receiving node needs to compare each row of its old table with the modified one. And if the next node entry is different, then fine, the receiving node chooses the row with smaller cost. If there is a tie, then old one is kept, means the old table that was there. If next node entry is already the same, the receiver node chooses the new row. These two are very important points which needs to be remembered while updating the table routing table. Okay, let's see with this particular example. You see that initially A receives from C. Oh, I have not saved. Okay, so this particular table, I will change it. This particular table is received by C, received by A from C. So you see, C has 240 infinity 4. Okay, now you see, to A2, to B4, to C0, to D infinity because C cannot reach D, and to E4. So A has received the routing table of C. Now what A does is, whatever values A has received, A has to add these values to the routing entry of A itself. So 2 plus, you see the value over here to reach from C to A is 2. So it will be added. So answer will be 4. Similarly, 4 is received and from C it is received. So 4 plus 2 is 6 over here. Similarly, C0 is received and from C it is the distance of A is 2. So 0 plus 2 is 2. Infinity plus the value received from here is infinity, and A's distance is 3. So infinity plus 3 is infinity itself. And finally, 4 is the cost that is received from C, and we had 2 as the distance. So the final one that is got is 4 plus 2, that is 6. So this is the A's modified table. Now A's old table, you see it has 0, 5, 2, 3 and infinity. Now what you have to do, you have to compare A's old table with A's modified table, and whichever value is less you have to use. So 4 and 0, 0 is less, 6 and 5, 5 is less, 2 and 2, fine, you just enter the same value. Here infinity and 3, the empty field is infinity. I will update and send you the PPT. Infinity and 3, so infinity and 3, 3 is less, and then finally 6 and infinity, so the value is 6 over here. Okay, and you see there is a change in the next hop. So from A, if you want to go to E, the total cost involved is 6, and you have to go via router C. So this is how the updating is done in distance vector routing. Most important part, when to share. So there are two methods. One method says that there is a periodic update concept. The period depends on the protocol that is using distance vector routing. Okay, and second is triggered update. Now what happens in triggered update? A node sends a table when there is a change in its routing table, whenever there is a change. So there are two cases. First, a node receives a table from a neighbor, resulting in changing its own table after updating. Second is a node detects some failure in the neighboring links, which results in a distance that changes its value to infinity. So these two cases may arrive because of the triggered update. So based on that, we have very important, that is two node loops instability problem. You see, to understand, first, before going in this particular figure, let me first give you a glimpse about what two node stability problem is. So what happens when we discuss about distance vector routing? A problem with distance vector routing is instability. What does it mean? It means that a network using this protocol can become unstable. How? So let us understand in this particular figure that shows three nodes, X, A and B. So what happens at the beginning, both A and B, both the nodes know how to reach X. So X to reach, the distance is 2, and from B if you want to go to X, the distance is 4 plus 2, that is 6. Okay, so what happens suddenly may be possible at some point of time that is shown by the figure over here. There is a disruption in the link, and the link between X and A fails. So node A changes its table. Okay. And if A can send its own table to B immediately once updating the table, everything is fine. However, what happens that the system becomes unstable if B sends its data or its routing table before A sends it. So A has received the data before A sending it. So ideal situation could be that A, after finding that the link is broken, updated its table and then sent that particular table to B. However, it has not happened, and B has sent its routing table to A before receiving A's routing table. Okay, so what happens? The node A receives the update and assumes that B has found a way to reach X, because A already knows that there is no way to reach X from here. It senses and it finds that it assumes that there is a way that B has found to reach X. So it immediately updates. Now, what is happening over here? You see, every time A is thinking that to go from X, I have to send this packet to B, and B is assuming that to go to X, I have to send the packet to A. So every time the packet is moving from A to B and B to A. So there will be a case when the number because this 4 will be multiplied, will be added to their own tables every time this every time the routing table is shared between A and B. Okay, so there will be a case where A and B both the cost in routing table of A and B both will be infinity, and this is a major issue, and this particular issue is called the two-node loop instability problem. Okay, I am going to explain this again. Okay, so what happens initially, you understand that X, A and B, three different routers were there. So X knows that, okay, to reach X from me, that cost will be 2, and B knows that the cost will be 4 plus 2, 6. Now what happens? There is a failure of the link. So definitely when there is no reachability from X, so A will update the routing entry to be infinity to reach X. So now if A would have sent this particular data immediately to B, so B might have changed its table and everything would have been fine. But what happened now, may be possible that due to certain things that has happened on physical layer while transmission or data link layer, error control, flow control, whatever we have discussed so far. So what B does, B updates its routing table and B shares it with A. So what happens? A thinks now, A updates its table and assumes that B has found certain way to reach X. So what A has done, every time A has to send certain data to X, it will send that particular data to B. Similarly, B assumes that there is some, because A has accepted and it has changed its routing table, updated its routing table. A now assumes that B to reach X, B is the intermediate router, and B assumes that to reach X, A is the intermediate router. So every time they will share the routing table, this 4 will be added to their routing table cost column. Okay, so this 4 will be added and the packet will only loop in this particular, in these two nodes. So that's why the looping will go on until and unless A has value to be the cost value to reach B is infinity and B has cost value to reach infinity. At that particular case, it will be understood by both A and B independently that X is not reachable from me. Okay, so that will be the final case, and until that there will be a looping, and that is not required in the network. So this looping is known as two-node loop instability problem. Okay, there are solutions to it. Okay, so that we will see what are those solutions. So there are three basic solutions. One is defining infinity. So in defining infinity, what basically here we don't, if we say that infinity is not infinite in nature, but let us define it to be some finite value such as 100. Okay, so practically what happens, most implementations in distance vector routing assumes and defines the distance between each node to be 1 and defines 16 as infinity. Means you can go for 16 number of attempts. Okay, so the size of network in each direction cannot exceed 15 hops. So this is a good solution. However, second solution is also there, that is called split horizon. Okay, so in this strategy, instead of flooding the table through each interface, each node send only part of it. Okay, so through each interface in split horizon, what you do is, instead of flooding the table through each and every interface, you do one thing. Whenever there is a requirement, only send the part of it. Okay, and for instance, what happens, like if node B thinks that route to X is via A, why to publicize it? Why to advertise to A? Because A has already sent its routing table to B, so A knows that I have sent this particular table. So unnecessarily, if B sends that information to A again, advertise that, okay, I know that you are basically you are means to go to X, I will be taking you. So that is unnecessary. So in using this split horizon, we are trying to remove this particular confusion. So what could be the steps? So in step number 1, so node B eliminates this information, X information. Okay, then step number 2, this node A keeps distance to X as infinity because X is not reachable from A. In third step, what A does, it shares the information of not reaching X to B. Fine, everything is going fine. And in fourth step, B updates its table. And then in fifth step, you see B also knows that B cannot reach X via A. A also knows that it cannot reach X even by using the router B. Okay, so this is a stable condition that is required. So that's what split horizon that does. Now there is a third one that is called split horizon and Poisson reverse. So you see, if you observe carefully in second method, that is the split horizon method, it has one drawback. What is that drawback? Normally distance vector routing uses the concept of timer. So how it uses the concept of timer? So if there is no news about route within timestamp, okay, if A doesn't get any news, if B is not publicizing or advertising to A, as was observed in the case of second method, that is split horizon, in this particular case this becomes a drawback because A has its timer. If it will not receive certain information or update information from B, A will understand that there is not a requirement of B because B wants to disconnect from itself, so it deletes that particular entry, B's entry from routing table. That is a major disaster because B is connected to A and A is trying to remove that entry from its table. So this can be simply, although one example, let me take you one example. So like if B refrained from advertising to A, let us suppose. Okay, so node A cannot guess that this is due to split horizon. Okay, so what B does, instead of not sending data to A, not advertising to A, what B can do is B can send an information to A and keeping the cost column as infinity. What infinity could suggest? So infinity could be suggesting a warning in quotes. That warning could be like, do not use this value. What I know has come from you. So in that case also, B has informed A. That is mainly required because there is a concept of timer that also the protocol has to follow. And at the same time, A will not update because B has sent a warning saying that this infinity that I am sending with the value that I have, this infinity that I am sending with the destination in the second column, that is basically a warning that I have received this information from you. Please do not try to update your routing table. Okay, so these are the three important solutions with which you can be able to go for two node loop instability problem. Anybody, any doubt as of now? Okay, so with this we can go to our next topic, that is RIP, which is, I told you earlier also, it is an implementation of the intra-domain routing protocol called distance vector routing. Okay, so it is, as the name suggests, RIP, routing information protocol. Okay, it is very simple protocol based on distance vector routing. However, there are certain considerations. What is the first consideration? That in an autonomous system, we are dealing with routers and networks. They are connected by links. The routers have routing tables, networks never have the routing tables. The second consideration is considerations, or you may take this as assumptions of the RIP also. The second could be the destination in a routing table is a network, which means the first column defines a network address. So now, you see, when we were discussing about distance vector routing, the first column was the next ABCD. Okay, now in RIP, now implementations differ. That was just to let you understand what is the guidance of distance vector routing. But in case of RIP, the first column will be the IP address or the network address. Okay, third assumption is the metric used by RIP is very simple. The distance is defined as the number of links to reach the destination. That is basically the hop count. So the second column will be the hop count, the number of hops a particular packet has to traverse to go to the destination. So first column in RIP will be the number of will be the network address or IP address, and second will be the hop count. In case of RIP, the infinity is defined as 16. You see, we discussed in the solution also that infinity should be defined to a limited value. Otherwise, the guidelines of distance vector routing cannot be realized in real life. Okay. So what does it mean that any route in an autonomous system cannot have more than 15 hops? Okay. So that particular autonomous system must have minimum number of maximum 15 hops. More than that will not be traversed by a particular packet. And finally, the next node column defines the address of the router to which the packet, again the IP address. Okay, we will see with this particular diagram. Okay, this is the example of a domain that is using the concept of routing information protocol, that is RIP. You see, the figure here shows an autonomous system with how many networks? 7 networks. Okay, how many networks are there? 7 networks are there. And how many routers are there? 4 routers. 1, 2, 3, and 4. R4, R1. Okay. So let us observe and understand the routing table of R1. Okay. So the table has how many entries? 1, 2, 3, 4, 5, 6, 7 entries. Okay. And what does these entries show? That it shows the reachability of network in the autonomous system. Okay, so this R1 is directly connected to which two networks? One is 130.10.0.2 and 130.11.0. 130.11.0.0 and 130.10.0.0. So you see the first two entries are having 1 hops because it is connected directly to the router R1. And next, because since it is directly connected, it is there is no need to enter the third column, next hop address. Okay, now to send a packet to one of the 3 networks, okay, at the far left, there are 3 networks, 1, 2, 3 at the far left. If you want to send there, if you use R2, okay, then you see you have to go for 195.2.4.0, and that is using 130.10.0.1 interface. And similarly, if you want to go to R4, you have to go for 130.11.0.1 interface. Okay, so likewise, only the number of hops, the destination, and the next hop is entered in this particular RIP. Okay. Now we will go to the next protocol of intradomain routing, that is known as link state routing. To understand the philosophy of link state routing, it is a little bit different than distance vector routing. In link state routing, if each node in the domain has an entire topology of the domain, okay, please listen to my words very carefully, that if each of the domain has an entire topology of the domain, which consists of what is the entire topology, what it basically consists of? It consists of list of nodes and links. Yes, we have here list of all the nodes and list of all the links. Okay, how they are connected, are they directly connected or indirectly connected? That kind of connection I'm talking about, that we have discussed 2 lectures before, I think in previous lecture, direct and indirect connections delivery. Okay, and the most important part is the connectivity cost in terms of certain metric. Okay, that we will discuss what could be those metrics. Other metrics, one of the metrics could be the cost. Second metric could be the condition of the link. I can say LQI, link quality indicator. Okay, the condition of link, is it up or down? Okay, based on that also I can have. Now see, in distance vector routing, you are discussing the cost. The most important part in routing is how you are trying to model your this connectivity parameter. Okay, so in distance vector it was very simple. You just go for distance, and minimum distance ke basis pe you just try to create your routing table. Now here in link state, we are trying to find the state of the link. Okay, and trying to model our routing protocol based on what is the state, right? So the state could be up or down, the state could be the type of connectivity, LQI parameters, quality of service parameters, anything could be there. Okay, so here in this particular figure, if you see the this, so to let you understand, link state routing use Dijkstra's algorithm. I don't know if you know Dijkstra's algorithm, but we will discuss that. It is the shortest path algorithm. Okay, so we will see how it goes. And so what does it say? That if a particular node has the state of the link known to itself and all the nodes known to itself, then it can be able to calculate the metrics to each and every node in that particular autonomous system with the use of shortest path algorithm called Dijkstra's algorithm. Okay, in this particular figure, you see there are how many nodes are there? 5 nodes are there. Each node uses same topology to create this routing table, but the routing table for each could be unique, because I have been telling again and again that all the routers will not use distance. Some of them may use distance, some of them may use the other link parameters like state, condition of link like up and down, or other things that I told you like cost of traversing and all. Okay, so since the calculations are different, okay, but the topology remains the same. Okay, so this particular figure, if I want you to have an analogy, you can say that we have a city map available. This is my city map. Okay, and each and every person has that particular city map. Now what needs to be done? Each person, these persons are A, B, C, D, E. They may go from, according to their specific requirements, they may choose any kind of path. But the path that will be chosen, again, they will be sharing their path, so that it will not be like B takes certain path that is that goes from A, and A has not shared its information with B. So the minimum or optimum path will not be there if B does not go via A. So that sharing will always be there, whether it is any kind of protocol, doesn't matter. Now the question arises, how can a common topology be dynamic? I am saying that these all things we need to do in dynamic way, correct? So each and every node is sharing this topology and storing this topology, fine. But my question is, how can a common topology be dynamic and stored in a particular node? So this answer is very simple. We have this list of 4 different actions that we are going to do with the use of link state routing. So what are those actions? First, we are going to create link state packets. What are those link state packets? Creation of states of the link by each node. Okay. Then second, what we are going to do, we are going to disseminate the link state packets to each and every router. So this kind of dissemination where a node is sending its link state packets to every router in the network is known as flooding. This is a very important term. Okay. So flooding, what you are basically doing, this is a kind of multicasting, but I would not call multicasting over here, because you are sending each and every LSPs to different routers on different links. Okay, you are not using the same channel to send a particular, because in multicasting you are using the same channel to send the packet to each and every host or set of hosts. So first is you are creating link state packet. Second is you are flooding that link state packet to each and every other router in a particular autonomous system. Third, you are trying to form a shortest path tree. And finally, you are calculating the routing table. Okay, so how it is done, let's see. So first, when you create link state packet, so link state packet carries a large amount of information. What is that information? Node identity, why it is required to make topology, list of links. Again, links and node identity are required for making a topology. Third, very important, is sequence number. Why is it utilized? Why? Because it facilitates the flooding and distinguishing the new LSPs from old ones. Okay, and finally the age of that LSP is also there when you are trying to create a LSP. What this age tries to prevent, it prevents old LSPs from remaining in the domain. If you are old and if your age has expired, as was said by the protocol, you have to get diminished. So LSPs are generated on 2 occasions basically. One is when there is a change in the topology. It is very well documented and very well discussed in previous lectures also. Whenever there is a topology change, I have to do routing. So in link state routing, I have to create LSPs. And definitely on periodic basis also we have to do, because we want the updations to be done in the network. And definitely that updation in the network will be done by updating the entries in the routing table. Second is flooding of LSPs. So what happens in flooding? So first, the created node sends a copy of LSP to each interface. Then second, a node that receives the LSP compares with copy that it already has. Third, if it is newly arrived LSP and at the same time it is older, then that particular LSP will be discarded. And over here to discard that LSP. And if it is newer, it has arrived and it is found that this is a new kind of LSP that I have received. So the node discards the old LSP and keeps the new one. Okay. Third, very important, is the formation of shortest path tree. So now the LSPs are created, it is flooded, and the LSPs are with each and every one. Now the shortest path will be done. So as you all know, a tree is a graph of nodes and link. So wherein one node is called the root. So if in this particular figure, A wants to find the routing table of entry of itself, in that case, A will be the root node of that particular tree. Okay. Further, when a shortest path is defined as a tree in which shortest path tree is defined as a tree in which the path between root and every other node is the shortest. Okay, so what is the requirement? For each node, a shortest path tree is needed with that node as root, and we are going to use the algorithm called Dijkstra. That is basically, I think you might have heard this algorithm and worked upon it during your data structure lesson course. So this algorithm divides, what it does, it divides the nodes in 2 sets. One is tentative and second is permanent. Okay, we'll see with this algorithm. So in this algorithm, what it does, first it set root to local node and move it to tentative list. Okay, tentative list is the temporary list basically. Now we will see that tentative list is empty or not. If it is empty, there is no need, because there is no other node to process, fine, which we will just stop the algorithm. In another case, means if it is not empty, then among the nodes in the tentative list, move the one with the shortest path to permanent list and add each unprocessed neighbor of last move copy to tentative list. It is becoming very difficult to imagine, correct? So let's see one example. So the first step, we will see this particular example with the use of here, what you see, this link state, this autonomous system. Okay, A, B, C, D, E, both all are connected with each other. So first we make node A as root and move it to the tentative list as per the algorithm what it says. So with this, what happens, the permanent list is currently empty and tentative list has the node A. If you travel from A to A, the value will be 0. That's what the bracket 0 signifies over here. Now we move A to the permanent list. It is permanent written over here. I will change it. Permanent list and add all neighbors of A to the tentative list. Which are those neighbors? If you see, it is B, C, and D. Okay. So A is again moved to the permanent list, and we have in tentative list B. From A to B, while traversing, you will use the cost 5. From A to C it is 2, and from A to D it is 3. Similarly, now you are going to process node C, move its all the neighbors of C in the tentative list and move C to the permanent list, node D, then B. Fine. Because now the question arises, you may ask one question, sir, why have you not gone and you have moved B before C? It is because C has lesser cost value, that is 2 as compared to 3 and 5 for D and B respectively. So it is better to first utilize C and then next one, that is D, then B, and since E has more value 6, so it will be the final entry. And then you see finally we have permanent list A, B, C, D, E and tentative list empty. That means we have formed the final shortest path tree, starting by considering that node A is the root node. Okay, now once the shortest path tree is done, the next is the calculation of routing table from shortest path tree. Okay, so for this, each node uses the shortest path tree protocol, and then the routing table shows the cost of reaching each node from the root itself. So it is very much clear from here that it for A it is 0, B 5, 2, 3, 6. Similarly, it is written, and since while traversing C, traversing C is found to have a neighbor E, it is found that to reach E, C is the next router that needs to be there in the routing table for node A. Okay, so OSPF is the implementation of link state routing protocol. It is again an intradomain routing protocol based on the concept of link state routing. Now its domain is also an autonomous system. Okay, but there are certain terminologies that you see over here also in this concept of area. We need to understand in this OSPF what is an area. There are different terminologies like area border router, what is area 1, area 2, area 0. Okay, what is a backbone router, AS boundary router. Okay, so let us understand this particular figure. Okay, so what happens to handle routing efficiently and timely, OSPF basically divides the autonomous system of itself into small areas. Now what is an area? An area is a collection of networks, hosts and routers, but most important part is that they should be contained in the same area at the same time. All of the components, whether it is a host, router or network, they should be connected with each other. Now each and every area can communicate. Now first, before that, the area has two important parameters. One is the identification associated with it. You see area 1, area 2, area 0. Now area 0 will be given to the backbone router. I am going to tell you back what is that backbone. But before that, understand that if area 1 or a node in area 1 wants to communicate to a node in area 2, it has to go through a specially assigned router that is known as area border router. Okay, so area border routers of all the areas can communicate with each other. Okay, and these nodes can communicate via the area border routers. Now, another term is called backbone. So what happens that among all the areas inside the autonomous systems, they are connected by a special area called backbone area. Okay, so that is what is assigned with area 0. The backbone area will be always be the assigned as area 0. What backbone area does, so the backbone area serves as a primary area, and all other areas are the secondary, considered as the secondary areas. So why this backbone is needed? So if due to some reason the connectivity between a backbone and an area is broken, a virtual link between routers must be created by an administrator to allow continuity of function of backbone as primary ones. Okay, so the that's why this is known as area 0, because every time you cannot say that okay, backbone is there. If somebody finds in the routing table it is area 0, okay, it is the backbone, and it will be treated as. Next, AS boundary router is there. So one autonomous system can also be connected to other autonomous systems, but for that again specialized router is there, which are known as AS boundary router, autonomous system boundary router. Okay, with this we go towards the main important part, that is the metric. Okay, so in case of OSPF, it allows the administrator to assign a cost called the metric. Okay, we are not saying any other kind of cost like distance or throughput or delay. It will only be considered as metric. Okay, so what could be that metric? That metric could be based on the different types of services. Now, in previous lecture, I told you that you can decide your own routing mechanism. So that routing mechanism could be based on minimum delay, maximum throughput, minimum jitter, minimum waiting time. Okay, so that becomes your metric. Okay, how the network designer wants to route between the different networks or routers. So that will be that different types of service, and that will be known as metric. Next is there are 4 types of links that we have in OSPF: point-to-point, transient, stub link, and virtual link. We need to understand what are those links. So a point-to-point link connects 2 routers without any host or router in between. It will be a direct connectivity between 2 routers. What is a transient link? Transient link is a network with several routers attached to it. So a network will be attached to more than one routers with a link that will be known as the transient link. When you say a stub link, so stub link is a network that is connected to only one router. Okay, a link that is connected to only one router, that will be known as stub link. And finally, the virtual link. So you see, when the link between 2 routers is broken, the administration may create a virtual link between them, just for a temporary purpose. Okay, because creating link in itself is a major problem, and it involves a lot of exercise to be done. So it uses a longer path that probably goes through several routers. So it means administrator temporarily, if it is creating a virtual link, it means it should not work between only 2 or 3 or 4 routers. So let's try to find a path that can be able to traverse, or that can be able to go through each and every router or near to each and every router, so that using that virtual link, all the routers can be able to send that information to each other. Okay, this is the graphical representation of OSPF. This is one autonomous system. You see network N2 is there, network N1 is there, N4 is there, N3 is there, N5 is there. All those networks are connected by routers A, B, C, D, E, F. Okay, there are transient links. You see T1 link and T3 link. These are the transient links. There are certain direct links. Okay, now if you want to graphically represent in terms of OSPF, you can represent by this figure B and taking all these figures from the book itself. It's very difficult to draw these figures. So if you want to see more clear version of this pictures, you can go to your Forozen book. It is clearly given over there. Now, the next protocol that we are going to discuss is path vector routing. Now, before going towards the path vector routing, let us understand what are the limitations of intra-domain routing protocols. What happens basically, they cannot be able to used between different autonomous systems, that we already know. Why? Because they are not suitable for inter-domain routing due to their scalability issues. Both the protocols become basically intractable when the domain of operation becomes large. This is one of the reasons of them not being scalable in nature. So what happens? The distance vector routing is subject to instability. We have already discussed. Okay, 2-node, 3-node problem is again, there is an extension of 2-node problem that is called the 3-node problem. So because of that, there is an instability involved, and the link state routing needs a huge amount of resources. Like, because each and every router, although they are in the same domain, they have the same topology, they are trying to create their routing tables on the basis of their own specific needs. Some may create on the basis of minimum delay, some may create on the basis of maximum throughput, and so on. Okay, so because of that, they are not suited for inter-domain routing, and this path vector routing comes into the picture for this. So in this path vector routing, it is assumed that there is one node in each autonomous system that will be known as the speaker node. Okay, and that they will act on behalf of the entire autonomous system. What speaker node does, it creates a routing table and it advertises it to the speaker node in neighboring autonomous systems. Okay, so the speaker node basically advertises the path among themselves. Okay, on the basis of that, all the autonomous systems are connected with each other. You see over here initialization. Okay, so in the case of initialization, you see what we have, each speaker node can know only the, so here we have how many autonomous systems? 4 autonomous systems: AS1, AS2, AS3, AS4. Okay, here A1 is the speaker node of AS1, B1 is the speaker node of AS2, C1 is the speaker node of AS3, D1 is the speaker node of AS4, and each and every autonomous system has its own. Now you see, autonomous system has a table. Okay, because there will be only one table, that will be the routing table of the speaker node of an autonomous system. So A1 has its own table, B1, C1 and D1 respectively are having their own tables. So initially what happens, that each and every speaker node can know only the reachability of nodes inside its autonomous system. Okay, you see in A1's table, A1 knows only the information about A1 to A5, which are in its own autonomous system. Then comes the second part, that is called the sharing. So now what happens in sharing? A speaker in an autonomous system shares its table with immediate neighbors. So what will happen? Node A shares with B1, C1. Why? Because A is only connected to B1, C1. B1 will share with A1, C1. C1 will share with A1, B1 and D1. Okay. Likewise, D1 will share with only C1. So likewise, the sharing will be done. Okay. Then third part is the updating. So what happens in updating? Whenever a speaker node receives a 2-column table from a neighbor, it updates its own table by adding the nodes that are not in the routing table, and again by adding its own autonomous systems and also autonomous system that is sent by the table. You see, by the table you will be able to understand very clearly, when A1 receives some information from B1 and C1, A1 will so this if A4 wants to go to C2, then A1 will be able to understand that, okay, if I want to go to C2 from A1 directly, I have to go to C1. If I go via B1, it is possible, but it is not the shortest path. Okay, but it is possible. From A1 to B1 is possible, A1 to C1 is possible. Okay. Similarly, the updation will be done. Okay. Now, there are certain key points. First is the loop prevention that we have already seen, two-node problem, two-node loop problem. So what is happening over here when a router is receiving a message, it checks to see if its autonomous system is in the path list to the destination or not, because it is updating its own autonomous system also, and the autonomous system that is received by the neighboring speaker nodes. So in this way, looping, if it is involved, then that message is ignored basically. So it prevents the loop happening in the during the interdomain routing. Second is called the policy routing. So what happens when a router receives a message, it can check the path also. So if one of the autonomous systems listed in the path is against its policy, it can ignore that path. Okay, there are certain policies. See, we have different autonomous systems. They have different policy of operation. And every time it happens that an autonomous system wants to communicate with another autonomous system, they must be somewhere, I'm not saying fully, but somewhere inclined towards homogeneity of their operation. So it becomes very easy. So if there is a homogeneity in terms of policy, okay, I will do that. Otherwise, I will ignore that particular path. Okay. Then third, optimum path policy is there. So if you see this optimum path, how it can be defined, it is basically the path that fits the organization. Okay, so every organization, when their network designers are creating the autonomous systems, that will be created on the basis of what kind of path it wants to traverse. Okay, if an organization says the distance doesn't matter but the quality of link matters, in that case you see A1 can go to C1 not directly but via B1, because A1 finds that the link from A1 to B1 is good. Okay, and then B1 will forward it to C1. But if A1 finds that from A1 to C1 reaching C1 is somewhat difficult because of the link issues, it will not do so. So that's what we are trying to say, that the optimality is very much important, and that depends on the type of organization and their network design constraints. Okay. So these criteria, you see the last point, the security, safety, reliability, all these criteria are there, and interdomain routing is basically dependent on these all criteria. So BGP is the protocol that is an implementation of this path vector routing, and it is used. It was first used in 1989, and there are 4 versions that have been evolved. I think it is the 5th version that people are working on. BGP abbreviates to Border Gateway Protocol. Now in BGP, there are 3 autonomous systems. First is the stub autonomous system. So as we have already seen what is the stub link. In case of stub autonomous system, it has only one connection to another autonomous system. It could be like one small corporation or a small local ISP. Okay, so local ISP will be connected to its another regional ISP, something like that. If it is not getting connected to more than other local ISPs, in that case, it will be considered as a stub autonomous system. Second is multi-homed autonomous system. So in multi-home autonomous system, more than one connection to other autonomous systems are there. But again, it is still only a source or sink for data traffic. So for example, a large corporation is there that is connected to more than one regional or national autonomous systems. That does not allow transient traffic. So if transient traffic is there, we have seen that more number of links are connected. That is called transient link. And if that is not there, it is the multi-home autonomous system. And the third category of autonomous system is transit autonomous system. It is basically a multi-homed autonomous system, but it also allows transient traffic, and that's what it is called, transit autonomous system. So like national and international ISPs or internet backbones, if you visualize properly, those they are connected with so many transient links. So that's why it becomes the example of transit autonomous systems. Now how you define paths? I have already told you that you can define paths based on the different requirements of the organization. But we have 2 broad categories of those paths. One is well-known and second is optional attribute. Okay, so what is a well-known attribute? It is one that every BGP router must recognize. It is known by each and everyone. What is optional? It is the one that needs to be recognized by that need not be recognized. Whenever it is required, you do that. Now again, well-known attributes are divided into two categories. One is mandatory and second is discretionary. So what is mandatory? So it is the attribute that must appear in the description of a route in the routing table. For instance, three examples I told you, like origin, from where this packet is getting originated. What is the path of the autonomous system? What is the next hop to which I have to go? So these are well-known but mandatory attributes. Second is well-known but discretionary attribute. What is that? It must be organized by each router, but it is not required to be included in every update message. Okay. Now, next one is optional attribute. It has two categories. One is transitive and non-transitive. What is transitive? It is one that must be passed to the next router. And what is non-transitive? That must be discarded if the receiver node has not implemented it. Okay, so these are the attribute categories. Based on that, we define the different BGP sessions. Now, what is a BGP sessions? So the exchange of routing information between two routers takes place in a session. Okay, so that is done with the use of TCP. Okay, but BGP sessions are sometimes also referred as semi-permanent because it uses the concept of TCP connection. Okay. Finally, our topic goes at the final slide, that is called external and internal BGP. They are the two types of sessions. Okay, so what is external BGP? External BGP session is used to exchange information between two speaker nodes belonging to two different autonomous systems. Okay, so very simply speaking, if the border gateway protocol is implemented between two autonomous systems and there is an exchange happening between these two autonomous systems, then it is external BGP session. Internal BGP session is there when there is an exchange of router information between two routers, that is, which are lying inside an autonomous system. Okay, this is very plainly clear to all of you. So with this, we are basically completing our routing protocol topic and unit 3 as well. As of now, is there any doubt?